Danke and guten Tag. Fortunately, that's the end of my German, so I'm going to have to change. I'm going to have to transition into my my native mother tongue, I'm afraid. So let's hope this works. Okay, excellent. Good, so let me make sure the buttons work. Good, that's all fine. So yeah, my name is David Power. I head up the High Performance Computing Division at Boston, so I look after a lot of the storage solutions and cluster solutions that we work with in the group. And this is kind of a presentation I gave a while back when we did a roadshow with the Accelero guys. And really I was kind of setting the scene here for how high performance computing is kind of the test bed for a lot of technologies that evolve into mainstream and enterprise markets. So I'm kind of, during this presentation I'm talking about, even though this is a storage event, the real balance comes from actually having a truly balanced architecture. It's great having these NVMe capabilities, but unless you can deliver that performance to your client, to your compute server or GPU server, it's a very little consequence. So really I've spent a little time today talking about how we balance overall architectures and how critical that is in modern architectures as well. And my marketing team had put in a video at the start as well, which was of no real consequence. I think it shows different areas that HPC is now being applied in as well. So, let's see if we can move on to the next slide. Very good. So, when I started off in HPC, this was really kind of what people's expectation was of high performance computing. It was a guy with a ponytail and flip-flops, locked in a research environment, working on a couple of Pentium 2s or 3s, and conducting kind of scientific research in that sort of an area. Now, a lot has kind of happened over the last 10 or 15 years, and high performance computing has really diversified into becoming essentially an almost essential toolkit for most modern enterprises in terms of being able to develop products faster, being able to simulate them and model them more accurately, and reduce overall time to market with product as well. So I've put in the Formula One car as an example there as well. We work with a lot of the Formula One teams who essentially have moved from wind tunnels into simulation and design for the vast majority of their designing and protocol of their systems as well. So HPC is not to be confused with the historical view of high performance computing. It really is a critical component in a lot of enterprises and companies today. So I think over the years, one of the other interesting trends is that high performance computing has evolved really from the benefiting off the back of commoditized services and servers. So again, once upon a time back in the 70s and 80s, if somebody wanted access to a large, vast amount of computational ability, they were typically the reserve of large government organizations or large security firms who could afford these large Cray-based vector systems. And it was only around the 90s that we started to see people take more commodity-based systems. This is when personal computer was around and people were starting to use 386s and 486s at home. So one of my first clusters was actually based on these commodity systems, which was a group of Pentium 3 servers in essentially a coat-hanging closet connected together by megabit Ethernet. And we'd use smaller building blocks to create a kind of a scale-out environment that had the same computational ability as these large vectorized systems, but was a very much a much more cost-effective way of doing this. And again, so HPC is democratized across most of the industries today, but historically there's been a focus on the C in HPC, which is high performance computing, but that's not necessarily the case anymore. So I scanned all of the internet and I plugged it into a Kibana database and some Hadoop deep analytics, and it came out with this graph. Now, it's very complicated, so I'll spend a little time talking through it. In short, disks haven't evolved at the same pace of CPUs. So I think that's very well understood already at this event, and I'm only repeating what people have said earlier on. And we've also, of course, recently had the advent of the GPU as well. So this trajectory of where the speed of a disk comes in, it's almost off the chart altogether in terms of how fast a GPU can actually compose and access bytes and process bytes. So we have a little bit of a mismatch in our industries today. And what often happens as well is when you don't have balanced architecture, when I look at running large-scale simulations across clusters, this is the sort of speed up I'd be hoping to achieve across my entire system. As and when the back-end storage or even network isn't balanced correctly, we end up hitting this point of diminishing returns, and we have wasted CPU cycles and wasted resources across our system. So this is what can often be seen across many clusters that we go in and investigate and consult on today when they're not correctly architected and balanced. So, to again set the scene, there's a number of laws within kind of computing that kind of dictate how we should actually go about creating these balanced architectures. Now, Amdahl, these were his observations for a balanced system, and I think the interesting one here is the second point. So obviously the first one is purely a product of how much of your code can actually be parallelized. That's fairly obvious. The last one then is around the kind of memory bandwidth per instruction. But we also should ideally have 1 bit of I/O per second per instruction. Should be a kind of a target for a very well balanced system. And very, very few systems, especially in the top 500, even get close to this sort of a balance within their system. So what can we do about all of this? Of course, this is great. We've got a number of NVMe providers here today, and a number of products already that we've been speaking about that provide NVMe. I think all of these metrics have been well documented earlier on, but really moving forward, they're going to become a much more standard, commonplace component within most of the storage systems and even compute systems that we deploy on top of our systems today. And you can see there's an order of magnitude in terms of performance increase that we get from these devices. That's all good and well, but today NVMe there's still a little bit of a price premium on those devices. But fortunately today I pulled some information from Gartner and Hyperion Resources, and this year was the first year that revenues from SSDs exceeded HDDs worldwide. And the good news for kind of end users is that's actually driving the price of a gigabyte of flash right down, and we're expecting sort of parity with regards to HDD by the year 2020. So we're still on a good trajectory down. There's still plenty of cost that can be dropped off of NVMe. And it's going to continue as consumers ramp up their usage of NVMe's within the system. So I think what that means today is when deploying a storage solution, it might not always be an option to have the entire system full of just NVMe, but we can certainly put in a percentage of our storage platform as the hot flash tier or burst buffer, which will be able to cope with all of the I/O on it. And then of course build out the capacity side on top of standard HDDs as well. How storage is being consumed by end users is also evolving. I think once upon a time, if you go back to kind of the virtualized world and the VMware world, people were very much using centralized SAN systems, and this is mapping a block device to a virtual machine, formatting that in a file system, and that becomes the disk's I/O capability. Even in the HPC side, we've had very flat structure in terms of the overall storage architecture, and people would either try and fit all of their execution parameters within memory. That would typically be backed with a parallel file system, and once that data was then sort of no longer in use, it would be pushed off into tape, which is a very inaccessible way of storing long-term data. It becomes very unusable. You can't go back and do any sort of analytics on top of it afterwards, so it kind of just goes out there and it becomes quite inaccessible. Over the last number of years, and I think Felix kind of mentioned a bit of this earlier on during the Cobite discussion, but we're seeing a lot more diverse uses of storage. There's a lot of value that's being stored in researchers' data, and the ability to go back over it over the course of a project or a campaign means that you can extract more and more value and more meaning from your data over time. So being able to access your data all over the course of the project eliminates this kind of tape tier altogether. So we find that people are building large-scale storage solutions with possibly object-based storage at the back-end tier to facilitate large-scale online access to all of your campaign storage throughout the duration of a project. There's still a place, of course, for the parallel file system, but as object storage potentially gets faster and faster, or you have unified interfaces which can access either a parallel file system or an object, that tier sort of merges within itself as well. We're also starting to see kind of an interesting adoption of burst buffer technology, and this is where people are putting in their NVMe's mostly today. So we have this tier which comes straight from memory. That's usually kind of an NVMe tier where people can do a lot of their current I/O workloads on it, and that's then flushed down to the file system or campaign storage after all. So, I mean, this is good, it's evolving, but it's becoming more and more complicated, it's becoming more and more challenging to manage, and the solutions out there in the field are struggling to keep up with this sort of paradigm as well. But that's the direction that we're going, which keeps things quite interesting in the storage field. And again, I kind of mentioned this at the start, HPC is broadening out into the enterprise market. And one of the key areas that we're seeing huge growth and adoption in at the moment is around artificial intelligence and machine learning. So I think in big data and cloud, that's always been a kind of a good position for HPC. But now in the AI side, this is getting us into a lot more kind of enterprise opportunities than we would have had, say, in the past, that are all leveraging the same technologies that we're deploying for standard HPC clusters. So one of the good ones, we've done a number of projects with the automotive industry. Some of the capacities and quantities that they're describing around, essentially imagine having a fleet of your German BMW or Mercedes cars out there, each one with a 4K video, driving up and down motorway, capturing all of that data, sending it back to be analysed. You know, we're talking hundreds of petabytes here of data that could potentially be used for developing this level 5 autonomous vehicle capabilities. So that's a very interesting area. Data security and fraud protection. So again, we've got different IO profiles for all of these, but the long and short of it is large data sets with fast access to the data sets and low latency to produce immediate responses to any queries that it actually has. Healthcare diagnostics. So I was actually talking with, we're doing a bit of work with Oxford Nanopore Technologies in the UK, who were a company that are doing kind of long read sequencing. And I was getting into a conversation with them about, you know, okay, this healthcare and personalised medicine and diagnostics and all that is, you know, that's going to become more commonstead within hospitals up and down the country. But the more interesting thing I spoke about was, I asked him, what else can you do with all of this sequencing technology, and how, you know, where's the point where it becomes ubiquitous, where we can actually just go and sequence anything we want, anytime we want, as quickly as we want. So can I go into a restaurant and stick a sequencer into my steak and work out where it's actually come from on the spot? That's the kind of work that we're getting to. And the next one I asked is, how can I validate that a pint of Guinness is good everywhere in the world? So I challenged him with putting together a small personalised sequencer that can do that for me when I travel the world, and make sure that my pint of Guinness stays good wherever I go to. So that's hopefully coming further down the line. I don't know what consequence that will have on storage technology, but I thought it was an interesting use case. Then of course there's all this stuff around personalised marketing and natural language processing as well, which are all great areas. There's another company that we're working with who actually do real-time voice analytics for financial institutes and even jails themselves as well. So they're actually able to not just understand you know, vocabulary and dialect, but they can actually now start to understand slang. So they can pick out keywords and context when inmates are actually talking about stuff that they shouldn't be talking about through kind of learning and repetition, and then training the algorithms within the process of that, which I thought was phenomenal. So yeah, for all of this, of course, we need obviously lots of storage, but we also need an overall balanced architecture. So we need to be able to deploy you know, a balanced network across the system, cluster management side of things, software integration and applications, and you have this kind of circle of training, validation, inference, and then going back and reiterating over all of the data again. So we've got a number of solutions within our portfolio that address the sort of life cycle of AI data, and we're bringing out a number of products based on our vScaler platform, which I have in a couple of slides, which will actually simplify the deployment of all of these types of systems. The other thing as well is, as I'm sure the guys have already kind of mentioned, with these systems you can get like these DGX boxes and these supermicro GPU boxes with lots of localized NVMe storage within them, but they become a huge problem when you start to scale out into a production sort of manner. So having access to shared data sets, reducing the need for local copies on every single one of your systems, and having a central governance across all of your data sets as well is critical for when you start to scale up your AI environment. So yeah, the great thing, so we have fast storage, we have fast GPUs, and how can we sort of balance these two together? So one of the other components that we build into a lot of our products are the Mellanox or the May-based fabrics into our systems as well. So these have a capability called GPU Direct, which allows GPUs to directly access memory pieces of I/O from the fabric itself without having to actually be copied through the local kernel. And it also allows GPUs to do NVLink direct memory accesses across the systems as well for kind of a large unified memory space. So again, in terms of pipes that are able to move the I/O in and out of the GPUs directly from the storage, we need to balance it with RDMA capability and GPU direct capability within there as well. Okay. So, the pointer might have gone off for lunch. There we go. So yeah, I've kind of spoken about this, but again, some of the really interesting work that we've been doing in the autonomous vehicle industry, it's mind-numbing how much data that they're actually trying to process, but at the same time, to get these data sets that are known good input vectors for the actual AI to go and learn from requires a huge amount of actual manpower. So there's an organisation we're working with who are essentially taking these video feeds from cars just driving around towns in Germany, but the video is being captured at 30 frames per second, and we're driving for hours, and then a fleet of maybe 50 cars that are out in the field doing that. The first phase of the classification that they're doing on their data sets involves them sending out each individual frame to 200 or 300 users around the world to go and manually tag. So a user has to go in to each individual frame and actually tag, this is a car, this is a traffic light, this is a pedestrian, this is a dog, and it's a hugely time-consuming task. So we've been developing products for this area which can actually simplify this and make it easier to access through remote workstations and things like that. But there's a video here with some audio. I think I can kind of skip through it. It's just kind of talking about AI in sort of general around the automotive industry. So we'll skip right through that. These are some of the, I presume if you've seen an Intel presentation recently, you'll have seen these numbers anyway. There's some astonishing amount of data being generated by these guys. So that's great news for all the storage vendors out there. Okay, so we have, if anyone is kind of interested in any of the technologies that we've been speaking about here today, we have a lab facility where we allow customers to remotely access our systems and bring in their codes and benchmark their capabilities against our systems. So we have like a full flash system which can deliver, we flatline the DGX essentially with the Accelerobox box. We've got a 10-node EDR Skylake cluster. We have 8 AMD nodes as well on our cluster, which were actually based on some of the Formula 1 rule changes that were made recently, are actually quite a very, very good fit. And there's some great wins actually recently in, I think, the announcement of our first petaflop plus systems here in Germany over in supercomputing last week. So it's good that Intel has a little bit of competition, at least for pricing, sensitivity and support. But yeah, we have all of these in our labs. If anyone's interested in kicking the tires and seeing what our systems can do, please do get in touch. This was one of the, again, we took the system that Axel was speaking about, put it into our lab, connected it up to a DGX, and we compared it against all of the other AI systems that were out there. NVIDIA have this pod reference architecture thing where DDN, Pure, and I think there was NetApp were validated as one of their architectural products. So we took the numbers from those guys, even the web.io stuff, we took them and we essentially walloped every single one of them quite easily with room to spare. So I'm just waiting on bottlenecks now to give you some HDO or 200 gig links so that we can really see the true potential of this individual system. Okay. Very good. So yeah, on the vScaler side, so when we're talking about all of these individual components, a lot of the challenges and complexities come from actually integrating all of these technologies together. So I've been working on a project within Boston which has been spun out as its own organization called vScaler. And this started off as a HPC consultancy engagement, and it's quickly turned into a standalone product where we've taken OpenStack, which is a cloud-based, open source cloud-based environment, and built all of the capabilities that we've been using and deploying in the high-performance computing space into the actual platform. So we can now deploy and configure AI and deep learning environments. So to give you a kind of a use case of this, we support GPU pass-through and virtual GPU. So we're actually an NVIDIA Deep Learning Institute partner, which means that we deliver training on basics of CUDA, computer vision, deep learning fundamentals, and I have a number of PhDs in my group that go out and deliver these courses up and down the country. But one of the challenges that NVIDIA were reporting quite early on is that, and even end users were reporting, is that one of these GPUs, they're quite expensive. So they can cost up to $10,000 for an individual Tesla grade GPU. So when somebody's just testing or evaluating or trying to get familiar with a lot of the codes and technologies that are in use, it's a very expensive commitment to go and just give someone a dedicated card. Now with vGPU, we can actually split up that GPU into 16 or 32 smaller chunks, and give researchers these small individual systems that are configured with the same software stack that you'd see in a large-scale cluster environment, but it gives them the flexibility to go and learn at their own pace, try things out at a small scale, and then when they're ready, they can roll it out into a much larger production facility. So when we're doing courses around this, we'll use our vScaler platform to spin up maybe 30 or 60 different instances, but we'll only actually be using 1 or 2 GPUs in the background to provide users access into all of this capability. So it allows a good transition from the learning phase right into the kind of running at scale and production phase. All of this is available, of course, through a self-service portal. So the idea being that for somebody to get up and running with all of these frameworks, it shouldn't require them to be a Linux administrator or a Linux guru from the command line. We have these simple front ends that build in all of the application portals where the user can just pick and choose exactly what they want, and it's all automatically deployed for them. So we do the same across Big Data and Hadoop. HPC, we've built in all of the capabilities from OpenHPC and XCAT and Werewolf onto this platform as well. We can do lots of stuff around Kubernetes and Docker and other container orchestration engines as well. So a lot of the AI at scale products that we're actually putting out into the market and running things like inference as a service, that's all actually based on top of the Kubernetes platform. Behind the scenes, we use the unified parallel storage pools. We sit on top of technologies like Cobite, and that allows us to actually provide a unified interface into object storage, into parallel file systems, into NFS, and it just means that we can do everything that we need to do all under one roof within our product. Separately then as well, with a small public cloud that we've integrated the platform with, which means we can dynamically and elastically burst workloads out into our own public clouds. We can go from OpenStack to OpenStack in terms of bursting. And we've been working in the rendering space with AWS, where we can actually push our rendering workloads now out into the AWS cloud as well. So we can actually act as a cloud orchestration tool as well. So lots more coming in that sense next year as well, but that's just a taste of what we can do with vScaler. Make your life easy, essentially, if you're an admin. And then sort of around the project delivery side of things as well. So I think Boston will be well known for the kind of the ability to deliver supermicro hardware solutions, but we've built up a team that has a lot more capability within the organization as well. So the typical kind of HPC journey that users tend to go on is that we start off in our profiling center. So this is access into our cluster where we have a lot of the tools and technologies to allow people to run and assess the performance characteristics of their code and put it through different hardware configurations and storage configurations and get a feel for what the application I/O demands are. After that, we've actually got a dedicated team of Prince 2 practitioners who are dedicated to actually delivering large-scale deployments. We can actually work with teams in terms of delivering large-scale solutions. We have an integration facility, which means that we build up clusters in their entirety. So systems are racked and stable with switches, the storage, the software, the applications. All of it is actually built together in our facility before it actually goes onto customer site. And this means that we eliminate any sort of component interoperability issues that might occur when systems are just integrated on site together. It's a very common issue that we see, but when we do it in our facility, it means we can get things on site and they're into production a lot faster. We've also got a suite of tools that allow us to do cluster validation and health checks across the entire system. So you can imagine if you start off with, say, 100 nodes, but maybe some customers want to go to 1,000 nodes, how do we identify one small cable that isn't performing as it should across the entire system? That can hold up a big, large parallel job, especially if there's any sort of weights or barriers in it. So we've got a suite of tools that actually go through and do a full scan of the entire system. They check component level stuff for memory bandwidth, CPU floating point performance, node-to-node latency, node-to-node bandwidth, and give you back a kind of a traffic light symbol of green, green, gold, or red, depending on good, warning, or not healthy. And these are tools that we can give to our end customers as well to reuse over the duration of their life cycle to check and see if anything's deteriorated over time or if any engineer has knocked out a cable by accident when doing any sort of repairs on it. And finally, as well, we do full managed services around HPC as well. So if certain teams are restricted in terms of the local administration teams that they have, we can do full remote managed services around the platform and allow end users to actually just go and interact with their users, enabling them to go and do more science or more research or more modeling, as opposed to just doing the day-to-day churn of the administration. So we can do all of that stuff as well. Excellent, so I mentioned the Deep Learning Institute. So yeah, we're one of only a few elite partners in EMEA who can actually go and deliver this. I think we're one of the only ones. And yeah, it just means anyone that's interested in kind of going down this route of getting up to speed on AI techniques, we've CUDA programming, we've got experts within the organisation that can go and deliver courses for you around that as well. Okay, brilliant. And that's myself. I think I've even managed to finish a minute early.
Dave, you probably might want to